Hello everyone, welcome back. So today we want to learn about the derivatives of logarithmic functions. So our goals, first start with the most common logarithmic function, natural logarithmic function, which is ln. Then we'll talk about how to take the derivative of general logarithmic functions, which we'll see is very similar. And then we'll use something called logarithmic differentiation to take the derivative of some really complicated functions. We'll explain that as we go. So first, let's talk about logarithmic functions. Remember, we call the natural logarithmic function is y equals ln x. Remember, that's the same as log base e. So I'm over here just a second. So remember that y equals the natural log of x. That's the same as saying log of base e to the x. That's the same thing. We just call it ln for natural log. And remember that for natural log, you can't take any log of 0 or negative number. Let's actually go to Desmos really quickly. We'll look at that graph, and then we'll talk about how the derivative is related to it. There we go. So y equals ln x. Okay, so if you remember what this looks like, you've seen this before. So base your domain is all positive numbers. All right, can't take the log of 0. For example, try to do ln of 0, it's not defined, or ln of like -2, it's also not defined. Okay, it has this basic shape. It has a vertical asymptote here, and of course, also remember that the natural log of 1 or any log of 1 is just 0. So they all have basic logs share this x-intercept in common. So it basically has a really steep increase right here, then it increases really slowly here. Okay, as we go out toward infinity. Okay, now the derivative of this is, as it says, just 1 over x. Okay, so let's look at that graph and see if that makes sense to be the derivative. So this time, just type y equals 1 over x. Now, if you notice, this course has two sides to it. But for this, we're just ignoring this left-hand side because can't take a log of negative numbers. Let's see if this makes sense. So once again, what the function does, the red function, the logarithmic function, has a vertical asymptote right here at 0. So it's always increases really steeply. So it has slope of the tangent line is positive and has a very large value here. And then the slope of the tangent line always stays positive because it's always increasing. And then the slope of the tangent line slowly gets smaller and smaller, but never 0. And that's what we see with the derivative. Okay. So here, remember the derivative gives us the value of the slope of the tangent line at each point. So here we said the slope of the tangent line is positive, very large, as we see here. This goes to infinity. As we go towards 0, as x goes towards 0, the slope of our tangent line goes toward infinity, or the slope of the tangent line becomes almost like a vertical line, and that's what we see here, that same behavior, so it becomes really large. So yeah, the slope of the tangent line goes toward infinity, and then the slope, although it's always positive, keeps decreasing the further we go out. And that's what we see. Okay, so that's the derivative. Now, one other thing below, you see the next line, it says next rule, it says we take the natural log of the absolute value of x, then it's also 1 over x. And this is true for x as long as x isn't 0. Because here, if we plug in a negative for x, that's okay because the absolute value makes it positive. So in that case, the only value of that, we can't take x as just 0 itself. Okay, so actually, if I go back and graph that, let me actually turn both these off. So if I want to graph the absolute value, so y equals ln, I can either do it as type in abs of x. I probably need parentheses there for that. What's going on? Hold on just a second. Oh, there we go. Okay, use parentheses around the x. I forgot that. Okay, that's what it looks like, which is basically just the same as the logarithmic function. Just essentially, you have a mirror image over here on this side. Okay, And then if we actually just, let's look at the graph that has the same derivative, you see kind of the same behavior. We already looked at this side. This side is kind of the same thing. So here we're always, this side we're always decreasing slowly at first. So here the slope of our tangent line is fairly shallow, it's fairly small, becomes really steep, goes toward infinity this way, and that's what we see. So it's always negative. It's always, derivative is always below the x-axis, and the value gets more negative, larger in absolute value, the closer we get to 0. Okay. Then one more rule. So then what if we take the derivative of a natural log of the absolute value of x, or some function in general? So let's say we have this. Okay, so this is basically the chain rule. So if I use the same property you just used, natural log, the derivative of the natural log of the absolute value of something is 1 over the something, 1 over the u. And then using the chain rule is just u prime, the derivative of u. Okay, and once again, for the same thing, u can't be 0. And also, final notes is all the other rules of derivatives we've learned. So using the chain rule, product rule, quotient rule, higher order derivatives, all those apply to logarithmic functions. So everything we've learned before. Let's take a look at a few quick examples over here. Let's just say we want to find the derivative. Okay, so number one, let's start with something like y equals natural log of, say, 4x. Okay, something simple to start out with. Okay, so we do y prime, or dy over dx. This is the chain rule. So now the natural log of something, we know from this rule that's 1 over the something. Okay, then the derivative of the something, in this case 4x, the derivative of that is just 4. In this case, we also get just 1 over x. Okay, number two. Let's look at another one. Let's take a look at something that involves this third rule. Okay, so let's say here, let's say our y is going to be a natural log of the absolute value of x squared. Okay, and once again here, of course, x can't be 0. Or actually make it x cubed, not x squared. Make it more interesting. Because you know the x squared can never be, x squared can actually be negative in places. So x cubed can be negative in places. Here we're taking the absolute value of that. Let's do this. So then our y prime, okay, so the derivative of the natural log of something is going to be 1 over the something. Okay, so 1 over x cubed. All right. Then the derivative of the something, the chain rule, derivative of the inside, the derivative of x cubed is 3x squared. And so what we get then is going to be 3x squared over x cubed. Same thing we have here. Okay. And then, of course, simplify. And that's just going to be 3 over x. Cancel out 2 x's there. Okay. Now, let's take a look at something else. So remember, we can always, and as I said before, always use these same rules of derivatives if we have more complicated functions. So let's say we have f of x is equal to, so this time we have x cubed times the natural log of x. Okay, so this, you can use the product rule. And so f prime then is going to be, doesn't matter where we start first. So if I do the derivative of x cubed, that's 3x squared times the natural log of x. And then plus, and then the derivative of the second function, the derivative of the natural log of x is now 1 over x. And then times just the first function by itself, x cubed. And now simplify if I can. The first expression can't really simplify. There's nothing I can combine. I'll just write as 3x squared times the natural log of x. And this, we have x cubed over x, which is going to be plus x squared. Okay. Now, let's look at something else. So something else we want to do is actually, let's look at this next example, or next couple examples. This time, let's say my f of x is going to be the natural log of x plus 2 over x minus 3. Okay. Now, a couple ways I can do this. One thing I can do is I can actually use essentially use the quotient rule, so the chain rule, so the derivative of natural log first, then the quotient rule of this, for example, or product rule, okay? But what I'm going to do here instead is actually use the properties of logarithms. I'll just say of logs. This is true for all logarithms. Okay, so this is something you may want to review. If you haven't looked at logs at the time, go back and review them from algebra, or there's good videos online about just type in the properties of logarithms. You'll learn about these. But one of the properties is if I'm taking the log, any log of a fraction, I can break it up like this. This is the same thing as the natural log of x plus 2. And since it's a fraction, it'd be minus the natural log of x minus 3. Okay. Now, but also keep in mind, I can't distribute the log. So I can't, this is not going to be the natural log of x plus the natural log of 2. I can't do that. Now, why did I do that? Well, if I take the derivative, f prime of x, then basically this is what's called linear. I can take the derivative of each one of these separately, and that's going to make this a lot easier to do. Okay. So the natural log of something, okay, is going to be 1 over the something, 1 over x plus 2, and then use the chain rule. The derivative of x plus 2, of course, the derivative of 2 is 0. The derivative of x is just 1, minus the natural log of 1 over natural log of x minus 3 is just 1 over x minus 3. And then, of course, the derivative of the inside part is, once again, like this one, it's just going to be 1. And so my derivative is just 1 over x plus 2 minus 1 over x minus 3. Now, this would be a good thing for you to try on your own. Use chain rule and the quotient rule, see if you get the same thing. And one thing, if you do that, you'll probably get something over one fraction. You can do that if you want to combine these into one fraction, but here we don't need to. But this is often a faster and easier way to take the derivative of the logarithmic functions if you use the properties of logarithms to help you out. Okay, number 5, one more like that. So this time, let's say we have y equals the natural log of 2x plus 7 to the 5th. Okay, now once again, I can do this, and I'm actually show you both ways to show this does work. Okay, so first way, let's do it the way we've been doing. So let's call this y prime this time. And so, and also be clear, this is the natural, take natural log of 2x plus 7 to the 5th, this whole thing. So the derivative of the natural log of something is 1 over the something. So 1 over 2x plus 7 to the 5th. Okay, now, then from the chain rule, the derivative of 2x plus 7 to the 5th, bring the power down, so it's going to be 5 times 2x plus 7. Subtract the power 1 from the power of the 4th. So I'm almost there. Then we have to do then, or still the chain rule again, the derivative of the inside. Derivative of 2x plus 7 is just 2. Okay, let's put all that together, simplify. And so our constant up front is going to be 5 times 2 is 10. Then we have 2x plus 7 to the 4th over 2x plus 7 to the 5th. Of course, we can cancel out all but one of these down here, and what we're going to be left with is 10 over 2x plus 7. Okay, that's y prime. Now, let's actually do that same one another way. I'll just say, or use, once again, the properties of logs. I'll just abbreviate that. And what I'm going to do then, let's start again. So y is 2x plus natural log, sorry, 2x plus 7 to the 5th. Y is the natural log of that. 2x plus 7 to the 5th. Okay. Now, one of the properties of logarithm says if I have an exponent here, I can take that exponent and then bring it down front. Okay. So that means that y is equal to 5 times, let's use in one place, 5 times the natural log of 2x plus 7. Okay. Now, let's take the derivative of this, so y prime. So constant just comes up front, kind of passes through. So 5 times the natural log of something is just 1 over the something. That's going to be 1 over x plus 7. Put parentheses around that for now. And then the chain rule derivative of 2x plus 7 is just 2 And now, as you see, we get exactly the same thing, but actually a little bit faster. 5 times 2 is 10 over 2x plus 7. Okay, so that's one reason why it's often helpful to use these properties of logarithms. Often it makes it a lot easier to take the derivative. Okay, now the next thing I want to take a look at is what if we have a different log? Instead of log base e, the natural log, what if we have other logs? As we'll see, we essentially have the same process. Okay, so let's actually make a line here. All right, so now I want to look at general, I would say general logs or general logarithms. So other bases. Okay, so once again, hopefully you remember from algebra class, okay, if we have something like this, log base b of x, where b has got to be positive and also b can't be 1, then basically it's exactly the same rule, except down here, if you notice, we take the log derivative of log base b, we have to multiply x times the natural log of b, okay? And remember, the natural log of this b, your base, that's just a constant. Natural log of any number is just a constant, okay? And so that's what we use here. Okay, and basically these properties are simply just the properties we saw before. We're just replacing the natural log with a log base b, and then down the denominator, then we have a natural log of the base itself. Okay, and actually, if you want more information, this actually kind of comes from something called the chain of base formula. You may have seen that for logs also. It kind of comes from that. We're not going to go into that here, but that's where it comes from. Let's do a quick example of this to explain why this is true, part why this is true. If we do, we have y equals, let's write the natural log of x. Let's write it this way, is log base e of x, okay? And then y prime, using this new rule, so we'll see this, our previous rule is just an example of this. That's going to be 1 over x times the natural log of e, okay? Using this, so then times the natural log of base down here. And remember, the natural log of e is equal to 1. Okay, you can check that with the calculator if you want. The natural log of e is equal to 1. And so this just becomes y equals 1 over x. Okay, so we see that the rule we used before is just an example of this. Okay, but the most common base you're going to use is a common log you're going to use is natural log. So that's why it's most important to know that one. Okay, just a quick example or two of this. These are pretty straight. These are just doing the same thing. Okay, so let's find the derivative of a couple. So number one, let's say I want to do y is equal to log base 2 of 4x. Okay, so using this rule, all right, so y prime, or dy d over dx, is going to be 1 over the something, 1 over 4x. Okay, but also it's going to be times then the log of the base, natural log of the base. Okay, and then from the chain rule, then the derivative of 4x is 4. And so this is going to be 1 over x times the natural log of 2. Okay, so going to change, we now have this new constant, natural log of 2, beside it. Okay, and of course, if our base had been 5, we have the natural log of 5. Okay, so you can imagine any of these ones we did before up here, if we just use a different base. Let's say, for example, we'd done this one before, we redid this one here. If this has been like natural log of 2, natural log base, or sorry, log base 2 of the absolute value of x cubed, we just have a log base 2 down here, here, and here. Okay, that'd be the only difference. All the other properties work the same. Okay, we'll do one more quick one like that. So let's see, let's maybe do one like that. So let's say we have f of x is equal to log base 5 of, I think it's a little more interesting, the sine of x. Okay, Now here, this is also a good example of understanding logs. There are places where sine is 0, places where sine is negative. So you can't just do any log of sine of any number just where it's positive. But if we do this then, f prime of x, okay, so 1 over the log, any log is going to be 1 over the something, 1 over sine of x, but then times the natural log of that base, natural log of 5, okay? Then, chain rule, the derivative of sine of x is cosine of x, okay? And so this is going to be cosine of x over the sine of x times the natural log of 5. Remember, the natural log of 5 is just a constant. And then you also can do one more simplification if you want. Remember, cosine over sine is cotangent. This is just going to be cotangent of x over natural log of 5. Okay, so that's how those work. Now, the last topic we'll look at today is something called logarithmic differentiation. And this is a technique you can use when you have like a really complicated expression to take the derivative of. Let's repeat that, logarithmic differentiation. Okay, so the idea, so first off, let's start with give you a function, an example of why this is useful. All right, so let's say we have this for our y. So y is equal to x cubed times the cosine of x over the square root of x minus 1. Okay, now we could take the derivative of this with what we learned so far without using logs. So we could certainly use, but you notice it involved potentially the quotient rule, and also on top it also involved the product rule and be a fairly complicated expression and hard to do. So the good news is there's a way we can actually make this a little bit easier to work with involving logs. Okay, so here's our property, or here's how we're going to do this. So first, we're going to start with our function. We're going to take the natural log, or actually do any log you want, but the natural log is easiest. Take the natural log of both sides. Okay, so that's going to be the natural log of y is equal to the natural log of this whole side. So x cubed times the cosine of x over, now I'm also going to write this, if the square root, I'm write this as x minus 1, the 1/2. Okay, remember square root's the same as 1/2 power. Now, the reason we did that then is so we can actually, our next step then is use the properties of logarithms to simplify the right side. Okay, so I'll just say use properties of logs on this side. So this side, the left side, is still the natural log of y. Okay. Now, I have a fraction. So first, break up the fraction. How to work from the outside in. That's going to be the natural log of, I'm going to use parentheses or brackets here. The numerator, x cubed times the cosine of x, minus the natural log of x minus 1 to the 1/2. Okay. Now, keep simplifying. So this looks familiar. So we did in an algebra class. Here, I can use another property of logarithms. I can break this up. The plus, this can be the natural log of x cubed plus the natural log of the cosine of x minus the natural log of x minus 1 to the 1/2. Okay, let's do a couple more things. Let's also use our other property logarithms where I can bring the powers down front, make this even easier to work with. And so that's going to be the natural log of y is equal to 3 times the natural log of x plus, this one stays the same for now, the natural log of the cosine of x, then minus 1/2 times the natural log of x minus 1. Okay, now, so now I've simplified it using logs. You notice everything is basically here in a linear form, so it makes each part easier to take the derivative of. Now, I'm going to take the derivative of both sides. What I say over here is, of course, the derivative of natural log of y is going to be basically 1 over y times y prime. Okay, the chain rule, the derivative of y. Okay, or you can also write it as y prime over y, and then take the derivative of this side. So we have 3 times the derivative of natural log of x is 1 over x. Okay, derivative of the natural log of cosine of x plus 1 over the cosine of x times derivative of cosine, remember, is negative sine of x from the chain rule. And then here I have negative 1/2, and the derivative of natural log of x minus 1 is 1 over x minus 1. Looks like a minus 1. And then finally, the derivative of x minus 1 is just 1. Let's put all this together. So we have 3 over x. You notice this is going to be negative sine over cosine. This means negative tangent of x. And here we have minus 1 over 2 times x minus 1. Now, this is still equal to y prime over y. So we're not quite done. Okay. Take a minute, look at what we did. So basically what we did is made it much easier to take the derivative instead of having to involve a lot of product rules and quotient rules. Made it a lot easier. And now the last thing I want to do, now you're taking the derivative of both sides. So it says finally multiply both sides by y to get the derivative by itself. Okay. So because you want y prime by itself, so multiply by y. And what I mean is just multiply both sides by y. Okay, so these cancel out. Y prime is equal to y. And remember, y is our original function. Okay, so remember, y was this, what we started with. This is y, x cubed times cosine x over the square root of x minus 1. So that's y. And it doesn't matter if it goes in front or back. I was right the way it is. So 3 over x times or minus the tangent of x minus 1 over 2 times x minus 1 times x cubed times the cosine of x over the square root of x minus 1. And that is our derivative. It's still a fairly complicated expression, but that's certainly a lot simpler than trying to do it the other way. Okay, let's look at one more of those. And also one more thing to mention. Since we took, and I mentioned this here in my final note, since we took the log of both sides, this really only applies wherever this is positive. Anywhere this whole thing is negative or 0, then this can't apply. Okay, so that puts kind of a restriction on it, this trivial logarithm. All right, so number 2. So one more, a quicker one. So let's say this time we have f of x is equal to 1 plus x squared times this raised to the power of the sine of x. Okay, it's an unusual expression. Once again, this wouldn't necessarily be too bad the usual way. Let's try it again with using logarithmic differentiation. Okay, so first, and once again, you can use any log, but just take ln of both sides. So ln of f of x is equal to ln of this whole thing. And I'm actually going to use brackets here to make it clear I'm taking the natural log of the entire thing. Okay. And once again, of course, it only applies if this is anywhere this is negative or 0, this won't work. All right. So now let's simplify this side. Now, once again, I can do is I can bring my power down front. Okay. And so this is going to be the natural log of f of x is equal to sine of x times the natural log of 1 plus x squared. And also one reason we're doing it this way is this is a fairly complicated thing to do with this base like here. And also we have a power of x in the base and also the exponent. Those are fairly complicated to take the derivative of. Okay. Now, let's take the derivative of both sides. And so, I'll just ever take the derivative. And so that's going to be 1 over f of x times the chain rule f prime of x. Okay. And over here, then we do have to use the product rule. Okay. So I'll start with this, take the derivative of the first function first. So derivative of sine is cosine of x times the second function as it was. Okay, then plus, then the derivative of the second function, the derivative of that is going to be, I'll just go and write the first function by itself first, the sine of x, and then the derivative of this is going to be 1 over 1 plus x squared. Okay, then the derivative of 1 plus x squared, of course, the derivative of 1 is 0. The derivative of x squared is 2x. And so, actually, we're almost there. We just have to clean a few things up. And so, well, I still have to do a few things. So f prime of x, so let's multiply it by f of x. But yeah, not too much more. All right. So here we have cosine of x times the natural log of 1 plus x squared. You can only simplify that any. And this we can write as the sine plus the sine of x times 2x over 1 plus x squared. And then multiply both sides by f of x. To get f prime by itself. And finally, we have f prime of x is equal to this whole thing, cosine of x times the natural log of 1 plus x squared plus the sine of x times this fraction 2x over 1 plus x squared times 1 plus x squared to these things. Squeeze it in the sine of x, and that's our derivative. Still, once again, still a very complicated expression, but that is the derivative. A lot easier, probably a lot easier to do than we have to do it the other way. Okay, so what we've learned so far today is how to take the derivative involving logarithmic expressions. So we first learned how to take the derivative of just natural log of x, which is the one you're going to see in most. Then we looked at how to take the derivative if in case we have a more general logarithm, any other base. It's very similar, except in the bottom, we just have to multiply by the natural log of the base. And then finally, we looked at logarithmic differentiation, where if you have a complicated expression, how can I take the derivative of that? And often it's easy to actually take the log of both sides. One's going to have to assume that's only valid, which is only valid where the expression where f of x is positive. And then we can simplify the complicated expression using properties of logarithms, then take the derivative of both sides and get the y prime or f prime by itself and get the derivative. Thank you. Have a good day.